Here we will use acid-base reactions as a simple introduction to using curved arrows to describe electron movement in organic mechanism. While we need to think of chemical reactions as interactions between atoms and molecules that are moving, dynamic processes like this are not easy to recreate on paper. In this seemingly simple animation, the blue electron-rich species with a lone pair is attacking an electron-poor red atom, with the green group breaking off to avoid breaking the octet rule. While this is a very simple reaction, in the greater scheme of things, it is impossible to make even this brief animation in a short amount of time. We need an alternative method, which is where the curved mechanism arrows come in. Let's consider as a starting point the interaction between an electron-rich base, represented as B, with an acidic compound, labeled as HA. We need a method to describe their dynamic interaction that is easy to understand and that works quickly on paper. Here, the base and the acid are the starting materials that begin as stable compounds before they are mixed together. The base then donates its lone pair into the antibond of the HA bond, temporarily destabilizing the system as the materials transition towards products. The transition state is a theoretical picture of what the system looks like at the highest energy point. Completion of B to H bond formation and H to A bond breaking results in products. The original lone pair has become a bond pair, and the original bond pair has become a lone pair. For reasons to be developed, the products are often more stable than the original starting materials. That is a lot of information that needs to be transferred to paper without creating an animation. In any acid-base reaction, we need to describe how the electron-rich base interacts with the electron-poor acid to produce the corresponding conjugate acid and conjugate base. We must remember that orbital overlap is involved and that the non-bonding lone pair orbital from the base needs to overlap with the antibond of the H to A bond to get the reaction going. Sir Robert Robinson came up with the curved arrow to describe these interactions, and this is now the universal convention for describing dynamic changes in organic reactions. These arrows are now an understood way of communicating changes, and the arrow must flow from an area of high electron density to low, and not the other way around. Curved arrows are used to describe individual bond-making and bond-breaking events in chemical reactions. In polar mechanisms, one arrow will typically describe one bond being formed or broken. We use electronegativity values and the presence of lone pairs to identify electron-rich and poor areas. The arrows will always flow in the direction that electron density is transferred. The arrows show up in over 100 mechanisms in the undergraduate organic sequence, so getting comfortable with their use early is essential. Let's look at some examples of how to apply the curved arrows, beginning with a carboxylic acid reacting with sodium hydroxide. The products here are the sodium salt of the carboxylic acid as the conjugate base and water as the conjugate acid. Firstly, we need to identify dipoles and charges in order to work out which reactant is electron-rich and which is electron-poor. Here, the hydroxide with its negative charge is electron-rich, and the proton on the carboxylic acid is electron-poor. We add the curved arrows to show the electron-rich base donating to the proton, and the conjugate base breaking off to complete the process. In the next example, we have the lithium salt of an amine reacting with an alcohol. This results in a proton transfer to give the amine and the alkoxide salt as products. For the starting materials, the anionic nitrogen is identified as the electron-rich center and the proton on oxygen as electron-poor. The bond-making curved arrow then begins at the electron-rich nitrogen and is pushed to the electron-poor hydrogen. The second bond-breaking arrow describes the electronegative oxygen taking a pair of electrons to complete the process. In this third example, a terminal alkyne is treated with sodium amide. The result is the sodium salt of the alkyne and ammonia. The electron-rich center is identified as the anionic nitrogen atom, while the alkyne proton is known to be weakly acidic. The bond-forming arrow therefore begins at nitrogen and goes towards the alkyne proton. The bond-breaking arrow shows the sp hybrid carbon picking up the electrons from the C to H bond that breaks. Try to use the same process for each of these situations. Work out what the products will be and how the curved arrows should be applied to describe each reaction.